This is the fifth video in the Essential Extract Complex Analysis series. In this video, I'm going to talk about Laurent series and the residue theorem. For a list of all the topics covered in this series, see the video description below. The topics that I'm going to cover in this video are isolated singularities, Laurent series, meromorphic functions, and the residue theorem. I'm also going to give a number of example computations along the way. First, let's talk about isolated singularities and Laurent series. Let's suppose we're dealing with a function f which is analytic everywhere in a punctured disk around a point z0 in the complex plane. As I've indicated here, by a punctured disk, I just mean an open disk centered at z0 but with the center point removed. Anytime we have a function f like this which is analytic in a punctured disk around z0, we say that z0 is an isolated singularity for f. In this case, f of z can be written as a doubly infinite series of the form given here. Such a series is called the Laurent series for f of z about z0. This series is unique and it's absolutely convergent in the punctured disk on which f is analytic. We can classify isolated singularities into three types, depending on the Laurent series expansion of the function about the singularity. First of all, if the coefficients an are 0 whenever n is less than 0, then the Laurent series expansion of f is really a power series expansion, and f of z extends to an analytic function on the whole open disk of radius epsilon centered at z0. In that case, we call the isolated singularity at z0 a removable singularity. If some of the an's with n less than 0 are not 0, then there are two things that can happen. First of all, if there's a natural number capital N such that a sub minus n is not 0, but a sub minus little n is 0 for all little n's bigger than capital N, then we say that f of z has a pole of order n at z0. This is the case when some, but only finitely many of the an's for n less than 0 are non-zero. The other possibility is that there's no such integer capital N. In that case, the negative part of the tail of this series doesn't terminate in a string of zeros, and we call the point z0 an essential singularity for the function f. Now we're ready to give the definition of what it means for a function to be meromorphic. You might have noticed that I already slipped and used the word meromorphic in my previous video. Well, here's the definition. For an open subset D of the complex plane, we say that a complex valued function f of z is meromorphic on D if two conditions are satisfied. Number one, f has to be analytic on all of D, except possibly at a set P consisting only of isolated singularities. Number two, each of those isolated singularities has to be a pole of the function f. It's not allowed to be an essential singularity. By the way, removable singularities are not very important in this discussion. If we find a removable singularity for a function, it means that we can extend the function to be analytic at that point. Just like with analytic functions, if we have two meromorphic functions, there are various ways that we can combine them to create new meromorphic functions. Let's suppose that f and g are meromorphic on an open set D. Then it's easy to show that the sum and product of f and g are also going to be meromorphic on D. Furthermore, as long as g is not the identically zero function, then the quotient f over g is also going to be meromorphic on D. This is a little bit less obvious than number one, but it's true. By expanding f and g as a Laurent series about any point z0 in the set D, we can show that if f has a 0 of order m and g has a 0 of order n at z0, then, if m is bigger than or equal to n, f over g has a 0 of order m minus n at z0, and if m is less than n, then f over g has a pole of order n minus m at z0. Analogous results to this hold if f or g has a pole at z0. I'll leave it for you to think about what happens in those cases. Now I'd like to look at some examples. For the first example, let's look at the rational function f of z equals z cubed minus 1 divided by z squared times z to the fourth plus 1. The numerator and denominator are polynomials, and polynomials are entire functions. In other words, they're analytic on the whole complex plane. Therefore, it follows from the facts that we just talked about that f of z is meromorphic on the whole complex plane. Let's try to determine where the poles of this function are. In order to do that, we're going to need to know where the zeros of the numerator and the zeros of the denominator are. The zeros of the numerator are just the cube roots of 1, and if you watch the first video, then you know that those lie in the complex plane at the points indicated here. There are 6 zeros of the denominator if we count them with multiplicity. The 0 at z equals 0 is a 0 of order 2. The zeros coming from the factor z to the fourth plus 1 are the fourth roots of negative 1. Again, hopefully you watched the first video and you can recognize those as the points indicated here. Even though we're looking for the poles of this function, we want to know the zeros of the numerator and the denominator, just in case some of them cancel out. In this case, they don't, and that means that all of the zeros of the denominator of f are going to give us poles of the function f. Since z equals 0 is a 0 of order 2 of the denominator, that gives us a pole of order 2 of f. A pole of order 2 is also called a double pole. Since each of the other 4 zeros of the denominator is a 0 of order 1, each of them gives rise to a pole of order 1. Poles of order 1 are also referred to as simple poles. So in total, this function has 5 poles, 1 of order 2 and 4 of order 1. Just for fun while we're here, let's try to compute the Laurent series expansion of this function about the point z equals 0. There's not only one way to compute the Laurent series expansion of a function about a point, and it helps to be clever if you can. One thing that does help, though, if you're at a pole, is to start by factoring out 1 over z minus z naught to the order of the pole. Then whatever you're left with is going to be analytic around the point that you're expanding about, and you can find the Laurent series by just finding the Taylor series expansion of that function about the point. In this case, since this is a nice rational function, we can try to use some tricks. First, factor out the z cubed minus 1 piece and notice that the 1 over 1 plus z to the 4th piece is something that we can expand out using the formula for the geometric series. When we do so, we find that 1 over 1 plus z to the 4th is equal to the sum n equals 0 to infinity of minus 1 to the n times z to the power 4n. The radius of convergence of this series is 1, but we don't need to be too worried about that as long as it has a positive radius of convergence. The fact that it has a positive radius of convergence means that as long as we stay within the circle of convergence, we can factor the z cubed minus 1 piece into the inside of the sum and split it apart into 2 sums. All of those steps are justified as long as we stay in the region where the sum is absolutely convergent. When we do exactly what we just said, we end up with 1 over z squared times the sum n equals 0 to infinity of minus 1 to the n z to the 4n plus 3 minus the sum n equals 0 to infinity of minus 1 to the n times z to the 4n. Once again, as long as we stay within the region of absolute convergence of both of these series, then we're justified in splitting apart the terms and adding them up in any order that we want. If we add them up in order of increasing degree and then factor in the 1 over z squared piece, we can extract from this the first few terms of the Laurent series expansion of the function f about the point 0. That example was a lot of work, but it's pretty typical of what you have to do in order to find the Laurent series expansions of meromorphic functions about their isolated singularities. For the next example, let's consider the function f of z equals cotangent pi z. This function is going to be important to us in a minute after we talk about the residue theorem. Cotangent pi z is cosine pi z divided by sine pi z, and both the numerator and denominator are entire functions. That means that f of z is meromorphic on the entire complex plane. The only zeros of the denominator are simple zeros at points where z is an integer. By a simple zero, of course, I mean a zero of order 1. Since the numerator does not have zeros at those points, we conclude that the only poles of this function are simple poles at the integers. Let's try to compute the Laurent series expansion of this function about the point z equals 0. Since the point z equals 0 is a simple pole, we start by factoring out 1 over z. The function z times cotangent pi z is analytic at z equals 0. So what we'd like to do next is to find the Taylor series of this function about that point. We can find the first few terms of the Taylor series by taking the first few derivatives of this function and then thinking about what happens when you take the limit as z goes to 0. In other words, by using the method that you learned in calculus. That turns out to be a little trickier than it appears at first glance, but when you do it, you get that the first few terms of the Taylor series of z cotangent pi z about z equals 0 are 1 over pi plus 0 times z minus pi z squared over 3. If you need more terms of the Taylor series, you can take more derivatives and take the limit as z goes to 0. This is going to end up being good enough for the application that we have in mind, which I'll show you in a few minutes. And after we factor the 1 over z in, it gives the first few terms of the Laurent series expansion of this function. In a minute, we're also going to want to know the Laurent series expansion of this function around its other poles. The good news is that there's not much work left to do to find those expansions. Since the function f is periodic with period 1, for any integer n, we have that f of z is equal to f of z minus n. So substituting in z minus n to the Laurent series that we already found gives us the Laurent series expansion of this function about the integer n. Next, I want to talk about the residue theorem, but before I do, it's helpful to make one definition. Suppose we have a function f with an isolated singularity at a point z0. Then it has a Laurent series like the one that we've indicated. The residue of f at z0 is defined to be the coefficient a sub minus 1 of z minus z0 inverse in this expansion. The notation that we use to denote the residue is res of f comma z0. Now we're in a good position to state the residue theorem. First, let's go through the hypotheses of the theorem. Let's suppose that D is a bounded, open, and connected subset of the complex plane with a piecewise smooth boundary, and that the function f of z is analytic on D except possibly at a finite set of points, z1 to zk, all of which are isolated singularities. Let's also assume that f of z extends smoothly to the boundary of the region D. The residue theorem then tells us that the integral around the positively oriented boundary of D of f of z dz is equal to 2 pi I times the sum of the residues of the function f at each of its isolated singularities. This is one of the most commonly used theorems in applications of complex analysis. I'd like to take a few seconds to briefly explain the relationship between the Cauchy-Goursat theorem, the Cauchy integral formula, and the residue theorem. That way you can understand the differences between them. All three theorems are very similar. In the residue theorem, in the case when f is actually analytic on D, then there are no poles or essential singularities of the function in the region D, and the statement of the residue theorem reduces to the statement of the Cauchy-Goursat theorem. In the case when the function f is meromorphic but not analytic on D, all of the isolated singularities of f are poles, and the statement of the residue theorem can be deduced as a simple corollary of the Cauchy integral formula. However, even in that case, the beauty of the residue theorem lies in the simplicity of its statement. Having it in front of you causes you to focus on the problem of evaluating the residues of your function at its isolated singularities. Now, there's also a final case. If it turns out that f has an essential singularity somewhere in D, then the residue theorem provides a slight generalization of the Cauchy integral formula. If you remember our proof of the Cauchy integral formula from the previous video, then you might see how to prove this theorem. Suppose this is our region D, and let's list the isolated singularities of our function as z1, z2, and so on. Since D is an open set, we can put a ball around each one of these isolated singularities, and by making the ball small enough, we can do this in a way that they don't intersect each other. The function f will then be analytic in the region which is contained in D but outside of all of these balls. By applying the Cauchy-Goursat theorem, we have that the integral of f around the positively oriented boundary of that region is equal to 0. That means that the integral around the positively oriented boundary of D of f of z dz has to be equal to the negative of the sum of the integrals around the positively oriented CJs that I've indicated here. Next, we substitute in the Laurent series expansions of the function f about each of its isolated singularities z1 to zk. Here, I've written a sub n superscript j to denote the nth coefficient in the Laurent series expansion of f about zj. Also, I've taken the liberty of interchanging the sum in the Laurent series expansions with the integral over cj. We can do that because the Laurent series expansions are uniformly convergent on the CJs. Now, each one of the inner integrals is something that we know how to evaluate. This is almost exactly the example that we did when we introduced complex line integrals in the previous video. The integral evaluates to be 0 if n is not equal to -1, and negative 2 pi I if n is equal to -1. It's negative 2 pi I and not 2 pi I like we did in the example before, because here the orientation is going clockwise, and in the example from the previous video the orientation was going counterclockwise. That means that the inner sum over n just picks up the residues of the function at each of its isolated singularities, and it counts each of them with a weight of negative 2 pi I. Factoring that out to the front of the sum gives us precisely the conclusion of the residue theorem, that the integral around the boundary of D of f of z dz is 2 pi I times the sum of the residues. To conclude this video, I'd like to show you two more examples, which are both applications of the residue theorem. First of all, let's see how the residue theorem can be used to evaluate a definite integral from calculus. This integral can actually be evaluated using techniques that you learned from calculus. The denominator factors as a product of two irreducible quadratics, and then after using partial fraction decomposition, you can find nice antiderivatives for the two resulting pieces of the integrand. However, I'd like to show you another way to do this integral, which doesn't actually require you to find an antiderivative for the integrand. The integral is the integral over a real variable x, but if we want, we can also think about this as the line integral of the function 1 over 1 plus z to the fourth over the real axis in the complex plane. In other words, the integral, which I've called I, is the limit as t goes to infinity of the integral over the line segment lt from minus t to t on the real axis of the function f of z dz. Since we're working in the complex plane, for each t we have the option of continuing this path of integration by integrating back around the upper half of the circle of radius t in the complex plane. I've labeled that piece of the circle as ct. The function f of z is a meromorphic function, so as long as we don't try to integrate over its poles, the residue theorem is going to tell us the value of the integral over this closed loop. We already saw in example 1a in this video that the poles of this function lie at the fourth roots of -1, and there are exactly 2 of those inside of the region that we're integrating around, as long as t is bigger than 1. So as long as t is bigger than 1, by the residue theorem we get that the integral over the union of lt and ct of f of z dz is equal to 2 pi I times the sum of the enclosed residues. If we write the integral over lt union ct as the integral over lt plus the integral over ct, and then take the limit as t goes to infinity, we obtain this formula for I. I is 2 pi I times the sum of the enclosed residues minus the limit as t goes to infinity of the integral over ct of f of z dz. Now we just have 2 steps left. Number 1, I'm going to try to convince you that the limit as t goes to infinity of the integral over ct is equal to 0. Number 2, we need to compute what the residues of the function at these 2 points are. First of all, by the triangle inequality for integration, the modulus of the integral over ct of dz divided by 1 plus c to the fourth is less than or equal to the integral over ct of the modulus of the integrand. Let's think about how large the integrand could be. For points z on the curve ct, when you compute z to the fourth, you're going to land somewhere on the circle of radius t to the fourth centered at the origin in the complex plane. After you add 1, the closest that you could possibly be to the origin is at the point negative t to the fourth plus 1. That means that the smallest that the modulus of the denominator could be is t to the fourth minus 1, as long as t is sufficiently large, let's say t bigger than 2. That means that the integrand here is bounded above by 1 over t to the fourth minus 1 as long as t is sufficiently large. Once again, if t is sufficiently large, 1 over t to the fourth minus 1 is bounded above by 1 over 2 times t to the fourth. Sufficiently large here can be taken to mean t is bigger than 2. In that case, these inequalities are both true. Next, the length of the curve ct that we're integrating over is pi times t. So combining this with our bound for the size of the integrand, we get that the integral is bounded above by pi times t times 1 over t to the fourth as long as t is bigger than 2. This kind of argument where we bound the modulus of an integral by using the maximum modulus of the integrand times the length of the curve is called what's known as an ML estimate. M stands for the maximum modulus of the integrand, and L stands for the length of the curve. Remember, all that we wanted with this integral was to show that it tends to 0 as t tends to infinity, and now that's clear. Just to remind you, the formula that we had a second ago was that the integral I that we want to compute is 2 pi I times the sum of the enclosed residues minus the limit as t goes to infinity of the integral around ct of f of z. We've now shown that this limit is equal to 0, so the integral is just 2 pi I times the sum of the enclosed residues. So the last step that we need to do now is to compute these residues. For the problem of computing residues, I would encourage you not to rely on formulas, but instead to always try to think about what's going on. That's because sometimes you might be able to come up with a clever way to extract the residue of a certain function. In this case, we're dealing with a function that has simple poles. If a function f has a simple pole at z0, that means that its Laurent series expansion starts off as a sub minus 1 over z minus z0 plus a0 plus a1 times z minus z0, and so on. The residue of the function at z0 is this number a sub minus 1. So in order to determine what it is, we can just multiply both sides of this equation by z minus z0 and then take the limit as z tends to z0. That turns out to be a good way to proceed in this example. When we do that in this example, we get that I is equal to 2 pi I times the limit as z approaches e to the I pi over 4 of z minus e to the I pi over 4 over 1 plus c to the fourth, plus the limit as z approaches e to the 3 pi I over 4 of z minus e to the 3 pi I over 4 divided by 1 plus c to the fourth. It may seem like a pain to compute these limits, but one good piece of news here is that you can use L'Hopital's rule. Since both of these limits are 0 over 0 indeterminate forms, when we use L'Hopital's rule, they reduce to limits of 1 over 4 times z cubed, as z approaches e to the I pi over 4 and as z approaches e to the 3 pi I over 4. Now you can just substitute in those limiting values and add together the resulting complex numbers, and you find that the value of the integral is pi divided by the square root of 2. The kind of process that we've illustrated in this example can be used to evaluate a lot of other definite integrals, some of which can't be evaluated using techniques that you learned in calculus. For the final example, I'd like to show you how to evaluate the sum of the reciprocals of the squares of the positive integers. You may or may not have seen this before. Even though there are many ways to evaluate this series, the ones that I know all involve techniques which are beyond what we usually teach in our first and second semester calculus courses. Anyway, I'm going to show you how to evaluate this series using the residue theorem. We're going to use what we learned about the function cotangent pi z from earlier in the video. For this problem, the function that we actually want to consider is pi times cotangent pi z divided by z squared. The numerator and denominator are both meromorphic functions on the whole complex plane. So f of z is meromorphic on c, and we can see that it has poles at the integers coming from the poles of cotangent pi z and the zeros of the denominator. For each non-zero integer n, the function cotangent pi z has a simple pole at n with residue 1 over pi. We know that from the calculation that we did before. Since z squared is not 0 at a non-zero integer n, the function f of z has a simple pole at every such integer. To compute the residue of the pole, we can take the limit as z approaches n of z minus n times f of z, and we find that the residue at each non-zero integer n is 1 over n squared. At z equals 0, cotangent pi z also has a simple pole, but at that point the denominator has a double zero. That means that the function f of z has a pole of order 3 at z equals 0. We can extract the Laurent series about 0 by using the part of the Laurent series of cotangent pi z that we derived earlier in the video. When we do that, we find that the Laurent series about 0 of f of z begins as 1 over z cubed minus pi squared over 3 divided by z, plus higher order terms. This shows us right away that the residue of f at 0 is negative pi squared over 3. What we'd like to do now is integrate the function f around a large square s sub n, where n is a positive integer and s sub n is a square with sides parallel to the real and imaginary axes, which passes through n plus a half and negative n minus a half on the real axes, and is centered at the origin. As n goes to infinity, we're going to pick up the residues from all of the poles at f. Remember, f had residues with values 1 over n squared when n is a non-zero integer, and negative pi squared over 3 at 0. When we take the integral around Sn of f of z dz and then take the limit as n tends to infinity, by the residue theorem we get 2 pi I times the sum of the enclosed residues. The next step takes some work, but with a little effort you can show that the limit as n tends to infinity of this integral is equal to 0. Once you've done that, if you solve for the series that we're trying to evaluate, you find that the series is equal to pi squared over 6. This formula was first discovered by Euler in 1734 as the solution to what was called the Basel problem. Euler's method for discovering this formula was different than ours, and as I mentioned, there are many different ways now of proving that it's correct. In any case, it's a beautiful result. Well, that's the end of this video. Thank you for watching. In the next video, I'm going to be talking about analytic continuation, the argument principle, and other topics. If you enjoyed this video, please like it and subscribe to my channel for more.